Heisenberg's uncertainty principle states that you cannot know precisely the position and momentum of a particle at a given time. You can know one or the other, but not both. Aufbau principle says that as protons are added to the nucleus, electrons are also added to the orbitals at the lowest energy first. So Aufbau, they have to enter the lowest energy first. Hund's rule says that electrons do not pair up until they have to. So if there's an empty orbital, they're going to go to the next empty orbital before pairing up. And then Pauli's exclusion principle says electrons have to have opposite spins because they can't have the same quantum numbers. So as electrons enter, they would enter the 1s first because of Aufbau principle. Then we would have a down spin because each of these orbitals can hold 2 electrons. Then the 1s is filled, so it would go to the 2s, and it'd fill that one up. Then it would go to the 2p, and because of Hund's rule, there's an empty degenerate orbital next to it, so it's going to go there. After each of those orbitals have 1, then it's going to pair them up. When you're doing your arrows, you can do a half arrow like I've been doing, or you can do a full arrow. Valence electrons are electrons in the outermost principal quantum number. They usually only consist of s and p orbitals because your d's and f's are going to be lower in energy, which we'll see on the next slide. So when doing electron configurations are kind of like an address for our electrons, or a probable address. We would read it just like reading a book. We would start with the 1s, go all the way through the 1s. 1s can hold 1, 2 electrons. Then we'd fill the 2s, it can hold 1, 2 electrons. Then we'd go over to the 2p, which can hold 1, 2, 3, 4, 5, 6 electrons. We keep reading 3s, then 3p, then 4s. Then notice after the 4s, we're going to fill the 3d. The 3d can hold 10 electrons. If you forget that, you can always count all the way across the 3d and you'll come up with 10. After the 3d, then it goes back to 4p. So notice my valence electrons would be 4s and 4p. The d has a lower number in front. So for instance, sulfur, we would find it on the periodic table. And then we would start reading. First, we go through the 1s. So that's 1s2. So in the 1s, we have 2 electrons. Then we're going to go through the 2s. So 2s2. Next, I'm going to go through this 2p. So that's 2p all the way across. So that's 6. And then right here, that's 3s. And there's 2 of them. And then finally, I go to the 3p, but I don't go all the way through the 3p. I have 1, 2, 3, 4. So that's the electron configuration for sulfur, showing all electrons. You can double check an electron configuration or to figure out what element it is by counting up all of these superscripts. 2 plus 2 is 4, plus 6 is 10, 12, 16. 16 corresponds to sulfur. Go ahead and pause the video and try the next one on your own. Go ahead and do B and C. Restart when you have cadmium and nitrogen. Cadmium is here and nitrogen is here. So for cadmium, you should have had 1s2, 2s2, 2p6, 3s2, 3p6, 4s2, 3d10, 4p6, 5s2, 4d10. Notice I don't have any commas in there, so make sure you're not putting commas. Commas are going to be incorrect, and make sure that you're putting superscripts where they go. So nitrogen was much shorter. It should have just been 1s2, 2s2, 2p3. All right, so for D, D is an ion. Ions are the ones people miss more commonly. So before doing sodium ion, let's do sodium. So let's just pretend we had regular sodium. I'm going to pause the video and do your electron configuration for sodium. And then sodium is located here. Restart when you have sodium atom. So you should have had 1s2, 2s2, 2p6, 3s1. But this had a +1 charge. So if it's a +1, that means it lost an electron, and it's going to lose an electron from the outer energy level. So in this case, the outer energy level, we have the first energy level, the second, and the third. We're going to lose it from the third energy level, leaving us just with 1s2, 2s2, 2p6. And that would be the configuration for sodium ion. Going to do fluorine ion on your own. Restart when you have E. So fluorine was here. It was 2p5, but this is a negative ion, which means it gained an electron. So it should have the same configuration as neon, which is 1s2, 2s2, 2p6. Notice that sodium ion and fluoride ion both have the same configuration. They're what we refer to as isoelectronic. Same number of electrons. Your group 1A and group 2A metals are going to lose electrons to become like noble gases, and our nonmetals over here are going to gain electrons to be like noble gases. The tricky piece comes when it's a transition metal or one of these metals down here with variable charges, such as nickel. So if we were to do nickel's electron configuration, we would have 3D, 1, 2, 3, 4, 5, 6, 7, 8. Make sure you star this one, because ones like F get missed all the time on the actual AP test as well as individual tests in class. So when we're looking at it, it's a positive charge, which means we have to lose 3 electrons. We have the first energy level, the second energy level, we have the third energy level, and we have the fourth energy level. Remember that you must remove electrons from the outer energy level first. So in this case, that would be the fourth energy level. That's farthest from the nucleus. So I'm going to lose those electrons there. But that was only 2 electrons. I need to lose 3 electrons. So the third electron can be removed from the next energy level, which is the 3s. So this is going to turn into 3d7. Go ahead and pause the video and try G, H, and I on your own. Restart when you have your answers. So for zinc, this is zinc atom, but we wanted a +2 charge, so you should have omitted the 4s2. So that should be your configuration for zinc ion. Notice there's no 4s. Then phosphorus is a -3, so it's going to gain 3, and it should have the same configuration as argon. And then iron has a +2 charge. So anytime you're doing a transition metal, I would suggest doing the atom first. So here we have iron atom, but it's a +2 charge. So we're going to lose this 4s. So just 1s2, 2s2, 2p6, 3s2, 3p6, 3d6. Sometimes you can write the electron configuration shorthand, also referred to as kernal configuration. So if it says showing all electrons, you have to start with 1s, but if it doesn't specify, you can do shorthand. So how shorthand works is you're going to use the noble gas that comes before the element in question. So if we're talking hafnium, here's question 72, so we're going to go backwards. Xenon is in brackets. So this means it has the same configuration as xenon plus, and then we're going to start reading at 55. So that would be 1, 2, 3, 4, 5, 6, 6s2. Follow the atomic numbers at the bottom. We have 57 and then 58. So I'm going to go ahead and do all of my 58 to 71. So this is 4f and this is 5f. So 4f, if you count across, you're going to get 14. And then I'm going to go back and get these two d's up here. So that's 6s, so this must be 5d. And that's 5d1, 5d2. So that's my final answer. I also could have broken it up and said 6s2, 5d1, 4f14, and then another 5d1. Notice that these add up to my 5d2, so I can do it that way. Normally on all of my answer keys, I'm going to have them combined like I did the first way. But if you want to do 57, then go and do 58 through 71 and then come back to 72 and do it this way, you're more than welcome to. So let's look at one more. Here's radium. So looking at my noble gas, this is 88, so 86 comes before it. So I'm going to put Rn in brackets. And then I just need to get to radium, which is going to be 7s2. So that's going to be much shorter than it was a minute ago. I'm going to pause the video and try C and D on your own. When it says Z67, it's telling you the atomic number so you can find it faster. So for lead, you should have had xenon in brackets, and then 6s2. Then I'm going to say 4f14, and then 5d10, and then 6p12. Just like before, I can double check myself by saying xenon has 54, plus 2 is 56, plus 14 is 70, 80, 82, and 82 corresponds to lead. And then HO is down here. So that's 67. 67, the one before that would be xenon. Then I start reading, that's 6s2. In this case, notice I'm stopping in the middle of the F, so I have to account for this one. So that's 5d1. And then I'm going to go down to the 4f's. That's 4f, 1, 2, 3, 4, 5, 6, 7, 8, 9, 10. So that's my final answer for HO. I'm going to pause the video, try TC on your own. Remember, you're doing it shorthand. So for TC, we have krypton in brackets. Then we have 1, 2, 3, 4, 5, 5s2, 4d, 1, 2, 3, 4, 5. But this is a plus 2, so we need to lose these. So it just turns into 4d5. I'm going to pause the video, figure out what element this represents. Notice that there are missing pieces in this. This is what we refer to as excited state, because there is no 3s. Restart when you have your answer. So you have 2, 4, 10, 13. 13 has to correspond to aluminum. Notice though that is not the ground state. So ground state electron configuration would have been 1s2, 2s2, 2p6, 3s2, 3p1. So this would have been ground state. But when given an electron configuration, sometimes you'll be given an excited state. It can't stay in an excited state forever. It comes back down to this ground state. Go ahead and pause the video, figure out which element has this configuration. So looking at this periodic table, we have 54 for xenon, 56, 57, 62. 62 electrons corresponds to SM. Go ahead and pause the video and try this one on your own. Restart when you're done. So this one's a little bit trickier because it says you're a +2 ion. If you add these up, you get 10 electrons, which corresponds to neon. So there's a couple of ways of doing this. One way is saying, okay, well, if that's neon, and something had to have lost 2 electrons to become the same configuration as neon, magnesium would make a +2 charge and have the same configuration as neon. So it must be Mg +2. Another way of thinking about it is you can say, well, if this has 10 electrons and it lost 2, then it must have had 12 to start with, which is corresponding to magnesium. So using that same logic, go ahead and figure out which ion has this configuration. Just like before, we have 10 electrons. But this time, it's a -3 ion. So the only atom that would gain 3 electrons and have the same configuration as neon would be nitrogen. Or we can say that it gained 3 electrons to get this 10, so it must have started with 3 less, or 7 electrons. This problem's, you're writing the electron configuration for lead, showing only the valence electrons, so only those outer electrons. Go ahead and pause the video and see how you do on this one. So for lead, you would have had xenon, 6s2, 4f14, 5d10, 6p2, which we saw earlier. But we only want the valence electrons, which would be our s and our p electrons. So 6s2, 6p2. That's the answer that we were looking for. We don't want the noble gas, and we don't want these inner electrons. So go ahead and pause the video and figure out what's the most likely charge of this electron configuration. Looking at this configuration, we don't even need the periodic table. We just need to look and say, well, the 3s is full, but the 3p is not full. In order to fill this 3p, we would need 3 more electrons. So I need to gain 3 electrons, which would give me a 3p6 configuration. And when you gain 3 electrons, that's going to be a -3. We also could have looked on the periodic table and said that this was the same as phosphorus. And phosphorus most likely makes a -3 charge. Go ahead and pause the video and see how well you do on this one. Restart when you're done. So this one's bringing back some periodic properties. It says you needed silicon dioxide, but you didn't have any. So to replace it, they give you a bunch of other oxides. Well, silicon is here on the periodic table. So if you're looking for something that's similar to it, you're going to be looking for things that are in the same column or family. Aluminum is next to silicon. Next to it means nothing. Arsenic is not in the same family. Again, it's next to it and down. Sulfur is in the same row, which is only number of energy levels. And Sn is in the same family, so that's going to be our answer. You won't be tested on this, but each of our orbitals have different shapes. The s orbital is spherical in shape, and for all orbitals, as the energy level increases, the orbital gets larger. And nodes are just areas of zero probability of finding an electron. So we have our different energy levels. And we can see that the 1s is smaller than the 2s and so on, because each energy level is holding more and more electrons. The p orbital is going to be in a dumbbell shape, and there's 3 different orientations around the x, y, and z axis. That's why there's 3 of those sublevel, or 3 orbitals. The d is kind of a clover shape, and there's 5 of those. And the f is just complex. This is what they would look like, but notice that there's 7 different orientations. So that's why when you're drawing your energy levels, you would have 1 for the s, p always gets 3, d gets 5, and f gets 7. It's the number of electrons divided by 2. For orbitals with the same value of n, aka energy level, s is lowest in energy, f is highest in energy. Last thing you have to be able to do is figure out if things are para or diamagnetic. Paramagnetic means it has at least 1 unpaired electron. Having an unpaired electron causes it to be slightly attracted to a magnet. While diamagnetic, all the electrons are going to be paired and so will be slightly repelled by a magnet. So how you would do this is you would say carbon, and I would look and see where's its last electron found. So here's carbon. Carbon's last electron's found in the p. Specifically, it's in 2p2. So that's super important, being able to figure where's its last electron located. The p, as we saw a few minutes ago, has 3 different orientations. So that is my 2p. Then I would say, okay, well, how do those 2 electrons fill this 2p? Remember from the very beginning, we said that according to Hund's rule, electrons are going to be separated until they have to be. So I'm going to have 1 in each of those spots. So I have 2 unpaired electrons. This is an empty orbital, not an unpaired electron. If I have at least 1 unpaired electron, it's going to be paramagnetic. Helium, 1 more together. So here's helium. It's in the 1s2. Well, s only has 1 orientation, so that's my 1s. And I have 2 electrons in there. So notice I don't have any unpaired electrons. So this one would be diamagnetic. I'm going to pause the video and do zinc and arsenic on your own. So zinc was 3d10. So D has 5 different orbitals. So 1, 2, 3, 4, 5, 6, 7, 8, 9, 10. So again, it has 0 unpaired, so it's going to be diamagnetic. And then arsenic is 4p3. So P had 3. And that's 1, 2, 3. So it's got 3 unpaired electrons. Because it has at least 1 unpaired electron, it's going to be para. If you're only asked, is it para or diamagnetic, the easiest way to tell is, where's it at? The only way something is going to be diamagnetic is if it's in S2, D10, or P6. If it's in one of those columns, then it's going to be diamagnetic. All others are going to have at least 1 unpaired electron. So carbon, it's here, it's paramagnetic. Helium is here, diamagnetic. Zinc here, diamagnetic, and arsenic here, paramagnetic. If I asked about calcium, it's in this column, must be diamagnetic.